If someone has a question, feel free to raise your hand. Yes.
Two questions. One for Dimitri, one for you, Fisher. Dimitri, you mentioned that on the far horizon, it's going to be a year and a half because of the bandwidth to get all the data back. Why didn't they do something so, given the risk that the thing may bust and not work, why isn't it more?
Yeah, so the question is why don't we have better bandwidth on the spacecraft there? And the problem is it's very very hard. I mean, it's so far away. You're kind of limited by the power that you can send back. You either have to have a bigger antenna. You're at a point that's I think Pluto's about 33 astronomical units away, meaning that the amount of light that we receive from it, which is what radio is when we're beaming it back, it drops by about a factor of 1,000 by the time it gets to us. So the power is so low that you have to transmit slowly so that you can detect it. So there was the spacecraft itself is powered by a nuclear battery, basically, like we have on the Mars exploration rover, that or Curiosity and everything. So that's about the best we can do to provide as much power as possible out there, and so we couldn't do much better. The Voyagers had the same issue.
Yeah, so the question is, are the super Earths rocky or are they gaseous? It turns out that the computer models can give you a whole range of different properties for these super Earths. And so depending on where in the solar system they form, and I mean, it's unlikely that these super Earths form this close to their parent stars. They likely form further out and then migrated in. And but depending if they formed really further out, then they might have the opportunity to gather more lighter elements, whereas ones that form slightly closer in might might not have been able to get as much hydrogen or water, and depending on how where they migrated, they might. It turns out that most of these are probably large enough that any atmospheres that they formed with, they probably wouldn't have lost too much of their atmospheres just because the gravities are larger. But again, it all depends on the particular scenario. And so you can have super Earths that are kind of edging towards becoming Neptune-like objects where you have big atmospheres. You can have super Earths that are giant water worlds in the sense that water makes up most of or a significant portion of the mass of the planet. So you might have water, like almost an Earth's mass worth of water or more. You'd have oceans extending down tens of thousands of kilometers, which is kind of a crazy idea to think about. And then you have these other models where you have iron worlds where most of the material is metal, or you have silicate worlds, like we saw earlier in that slide, or diamond worlds, or you have mixes of those different materials. So these super Earths, at least theoretically, are turning out to be a very diverse type of planet. And whether that pans out when we have instrumentation to start detecting them spectroscopically, that's another question.
Wouldn't those inner oceans make a planet sort of wobble? Would be sloshing around in there?
So the question is, would these worlds of giant oceans make the world wobble, with all that water sloshing around?
Like
It,
a balloon,
yeah, like a balloon, you would expect the surface to slosh as it orbits. And I haven't actually examined the math, but my first inclination is to say that that probably wouldn't happen, just because the gravity would hold the water down enough. I mean, if you had a moon that was relatively large, it could raise tides on that world. But
but they're inside, the water's inside.
I mean, one way that you know, that the water could your world might not be perfectly spherical is if the planet was rotating sufficiently fast. enough that through centripetal or centrifugal forces, the equatorial region would actually be wider or larger than if you measure the planet from pole to pole. So that could be one example where a water world would have like a fat equatorial belt. But I can't imagine a scenario where the water would slosh around. Can you, Dimitri?
Yeah, you kind of need another body, like Kachin mentioned, like having the moon and stuff. So our Earth, has a fair amount of water on it, and it does slosh around, and that's because the moon is there. But and it rotates as well. So you need, given an empty space, you have something rotating. It's just it becomes stable, and the rotation would cause bulging at the poles and such. But you can add uneven heating and things like that, which would be a possibility of creating turbulence in that, causing things to slosh about. So,
Can you guess what kind of water is inside that planet, or was it light, or
what state
is
is
it
that?
H2O,
So the question is, can we guess what sort of materials in that water, whether it is water? And it turns out that water is a very common material that you find throughout the universe. So we think the early solar system, our early solar system had it. We find it, we detect it in other solar systems that are forming. And in fact, much of our outer solar system, like Pluto, like the Kuiper Belt objects, like Europa, the outer moons of the giant planets, there's a lot of water in them, and that's because there happens to be a lot of water in the universe. So it's not surprising that these models predict that you can form water worlds, or worlds that have 20% of its mass made up of water. And I forgot what else I was about to say.
The kind of water it is. Water is.
Yeah, and water is water, and you might expect things to be mixed in to the water that might change its properties slightly, but for the most part, these computer models start with a lot of water in the simulation, and that's why you end up with water on these simulated planets, because we know there is a lot of water out in the universe. Yes, sir.
Kind of goes to the different things mixed in the water with the Europa in a can. Have they looked at different salts, such as potassium and magnesium salts, to look at the different colors produced?
Yeah, so the question is, have they looked at different salts, like potassium or magnesium salts, to see if they have different colors? And I am not an expert on this, but from what I understood reading the press releases, I wasn't able to get a copy of their actual paper, but I suspect they haven't done a similar experiment with other types of salts, at least in that particular setup. If you consider that they probably went out to the supermarket to buy their regular sodium chloride, although I don't actually know that because I haven't read the paper, and they might have done the easiest experiment that they could first, but I don't know for sure.
Question about Pluto.
Yeah.
Why is it so severely tilted on its axis?
So the question is, why is Pluto so severely tilted on its axis? We'll find a lot of the Kuiper Belt objects have either large ellipticities, meaning they're not a very circular orbit, or they're very tilted there. Most of those Kuiper Belt objects got put out into the Kuiper Belt, which is somewhat along our, the plane of the ecliptic, but it's somewhat dispersed there. But most of it's an ejection process where these were first formed in the solar system and ejected by, like Neptune and Uranus, basically, then moved them into the orbits that they were at right now. So you have a majority of things that are forming on that ecliptic plane, but then it gets broadened by that. And we have another, group of comets and things like that are even further out, called the Oort cloud, and those are at any inclination. They're in almost a spherical halo. I don't know if you have anything to add to that.
Yeah, and Pluto is actually in an orbital resonance with the planet Neptune. So you might remember that Pluto, the orbit is not perfectly circular. It's more elliptical than many of the other planets, although Mercury actually turns out to be the most elliptical of all the planets. But its orbit is, so you might think that because, and you might also remember that Pluto sometimes gets closer to the Sun than does Neptune because of its elliptical orbit, but because of its orbital resonance, Pluto and Neptune will never actually get close to each other, just because of the way the orbits are set up. So Pluto and Neptune obviously have had encounters in the past where they've had these dynamics that have shifted their orbits in such a way that Pluto is in this resonance.
I think Saturn goes around. I mean, Neptune goes around twice, and Pluto goes around 3 times.
Yeah, something like that.
In that resonance. Yeah.
I've always wondered.
The question is, why do like pictures of stars have the cross in there? Yeah. Well, what's happening, like the Hubble image that I showed of the pillars of creation, has those in the brightest stars. If you could look at the intensity of the, go back to that one. A little further back. Yeah, that one would have had it. Yeah, so there's one that has a cross right there. That actually has to do here with the fact that the secondary mirror of the telescope is out in front of the primary, and by diffraction of light around that causes some of the light that you're trying to focus at the spot of the star to diffract out of the beam and show these patterns. This pattern here is actually evident in every point source in there. When it gets faint enough, you don't see them. That's because the brightness of this is much less than the brightness at the center of the star. But that same pattern is in every single star, and it is due to diffraction of light.
Why at right angles? Why 4?
Well, because the spider mechanism that holds that secondary mirror is 4 struts that come in and hold that mirror. So in a lens system where you have like a telescope that you look like a spyglass or something like that, they will not have those structures on them. So that's actually one of the reasons that in small telescopes, when you look at planets from the ground, the refractive telescopes, the ones with lenses, are actually better to look at planets because there's less light cast away from the object that you're looking at, and you can get a little bit better fidelity. Okay, question way back there.
Yes, you answered half my question a while ago, but does Pluto, with the short time we're going to be able to use New Horizons on it, or they already, does Pluto have a precession?
Does Pluto have a precession? Yeah, well, where it spins around its axis like a top and everything like that. If it does, it'll be very, very slow. So I don't know the answer to that. I mean, we have our precession of the Earth. It takes 26,000 years, and I imagine it's on that time scale as well, with its interaction with Charon. And I don't know that we know that much about that kind of dynamics of the system.
I just wondered.
Yeah. So the basic question is, why does this look the way it does here? So like we can see some of those dark regions back over in here. These are dense regions there that in fact, this paper that I talked about did explain some of this here in terms of the orientation of the stars. So like this one here, we see a lot of emission from here, and that's because the star that is shining on this pillar is actually, we're seeing the side that is facing that star, and we're getting the ionization and evaporation from that surface. This is essentially in shadow from those other stars. So there's less of this happening over here, and that's actually one of the things that they talked about in that paper. Does that answer all of those things, or was there another?
Presumably, if you've got the dust distributed to start with evenly, and you've got this cluster shining light on it, and the cluster has lots of different stars, all of which are pouring light down, you would expect a relatively smooth boundary.
Oh, okay.
Instead, what we're seeing is very raggedy.
Yeah, very ragged. So it's because the gas and the dust is not evenly distributed. And so these pillars all represent points where the gas and dust was actually denser. And so I had explained the analogy like if you've seen Garden of the Gods, those rocks are standing because they were denser rock when they were first formed and have stood up better to the erosive forces of nature. This is the same kind of thing here. And so this, these areas up here are denser, and they point back to where these eroding stars are, and they are then essentially shielding the rest of the gas cloud that's behind them and putting up a good fight. Oh, I should say that one of the things in the paper there, so they were to look at the dynamics of the evaporation, and this particular structure has about 2 to 3 million years left, and it's gone.
Actually, I have one other comment. And the one other thing I want to point out is that all the stuff back here that you see that it all looks like just a nebulous glow, but what we're actually seeing is the backside of the molecular cloud. And so there's, the fact that you don't see background stars means that there's actually more gas and dust that's occluding the background stars in these directions. So there's even more gas and dust, also very dense and thick back here. And the reason why it has this sort of nice bluish glow is that gas is also being illuminated by those massive stars. So we're actually seeing in the far background another surface of this cloud. Yes, I think the waves and tides would be a kind of sloshing, definitely. But they're caused by a moon in orbit around us. So if a water world had a sufficiently large moon, or even actually a small one, yeah.
Right. Let's take one more question.
Well, when that spacecraft goes past Pluto and keeps going, I would think that it's going to bump into stuff in the Kuiper Belt. So wouldn't it be good to elevate it so it can look down on the Kuiper?
Well, so the question is, are we going to run into stuff in the Kuiper Belt, and is there a better vantage point? Things are there's the density of objects out there. There's like no chance that we're going to run into anything unless we know in that inner part of the Kuiper Belt. Getting above and looking down doesn't do us any better than when we're looking into it. We want to get closer to the objects. You can see that even now we've been 9 years in space here, and we're 50 million miles away, and the images are still not that good. You've got to get right up on those objects before you actually can get some useful data on there. So I mentioned there's a couple candidates that we want to go to. They have enough fuel for course correction, can deviate the spacecraft on the order of a few degrees. So as they continue to look and find objects, maybe there's a couple more objects that we'll be able to look at. No way we can get into orbit around them because there's not the kind of fuel that would be required to do that. So it's going to be another quick flyby, just like this one. But the spacecraft was designed to try to get as much useful data as possible in that time. So it stores it really fast, and then of course takes a long time before it can download it all. All right. Well, probably if we've got a few more questions, you can ask us in the back here, but we should let everybody else go. Thank you, and look forward to seeing you guys next time.